Welcome to our webinar. We're going to talk about the topic DAB contribution. So how to get audio from the radio studios to the head end. But before we start, let us shortly introduce ourselves. So starting with my colleague Tork.
Hello, everyone. I'm Tork Nienhoff. I'm working as a software developer, and I'm responsible for our DAB product range. I have expertise about 12 years for DAB. I'm a member of the technical committee for from World DAB. World DAB is maintaining the DAB standards. And we have a lot of DAB products built up in the past 12 years. We started with EDI over satellite from Telenor Norkring and EDI ETI converters, but now we have also a lot of other products in the DAB range, for example, DAB audio encoders or DAB monitoring, and we will show you that in detail in the next minutes.
Yes, and I'm Arne Borsum. I'm product manager at 2WCom, and I'm also a DAB expert. I've worked in that field for since 2015, but even before that, during my time at Fraunhofer, I worked on audio for broadcast applications, which also included DAB. I'm also a member of World DAB Technical Committee and the committee for the SNIC committee for spectrum and network implementation. So yeah, let's continue with our webinar. Have a short look on our agenda. We'll start with some general remarks about 2WCom and DAB, but we'll then quickly jump into the challenges and considerations of getting content from the radio studio to the head end. We'll also have a look on our product portfolio of hardware and software products before we will cover the two main methods of audio contribution more specifically. So firstly, using audio over IP, and second, using dedicated DAB+ encoders. This will also include demonstrations, which Tork will show, including the user interfaces of our solutions. Before we finally come to the conclusions and questions, we will also cover additional possibilities of audio sources which can be used for DAB in our products. On the questions and answers, I invite you to write your questions in the chat of this webinar, and depending on the time remaining at the end, we will try to answer all questions. Yeah, let's talk about our dedication at 2WCom for DAB. We are dedicated to advancing DAB and offer pioneering solutions to empower broadcasters to optimize their audio delivery and distribution processes. We do continuous innovation, refine our products, and give our customers access to latest advancements in technology. But we also look at the specific requirements and needs our customers have and propose tailored solutions and designed to address their specific challenges and requirements in DAB setups. Having a look on that typical DAB infrastructures, we have solutions everywhere where interfacing between different parts of the system setups is involved. I don't want to jump into details here, but I just want to show that the central element of a DAB system setup is, of course, a DAB head end. And where 2WCom has solutions for is interfacing the DAB head end with the studios at the delivery side and at the other side with the transmitter network at the other side. So summarized, we have solutions for DAB distribution. This means distributing EDI streams to the transmitter network, whether it is over IP satellite or even over unstable networks using SRT. And our solutions guarantee reliable and efficient distribution to the transmitters. Studio-to-Headend delivery, whatever the preferred method of transporting your audio is to WCOM, has a solution tailored to your needs and ensures seamless delivery from Studio-to-Headend. And this is also what we will have a deeper look on today. I'm coming to some examples where 2WCOM has helped implemented DAB. The first one is in Norway, where a high number of transmitter stations is paired with EDI feeds from the headends. So token was involved, so you can maybe talk a bit more about that.
Yeah. This was a very successful project, and over thousands of our FlexExec devices were placed over Norway. They were used as these low power gap fillers, so Norway had to do 90%, over 99% coverage to shut down the FM network, and they did that with this many low power gap fillers. So these low power gap fillers basically received EDI through satellite and distributed that EDI to the DAB transmitters, which had a short range of some kilometers. And that was a really good proven example that EDI over satellite distribution can be successful and helped Norway to fulfill their needs to shut down the FM and to maintain high coverage of DAB services.
Yeah, second example is in UK, where 2WCOM provided Akiva with the audio contribution system and the DAB distribution gateways. Yeah, Talk is also deeply involved, so we can also say some details.
Yes, that's actually this Akiva project has been the largest project for DAB rollout in the last recent years. So I will show you the setup as a first demo in detail. So basically what is special to that is that the audio distribution is just normal audio over IP distribution, which I will show you as an example, and that audio over IP distribution is used with our IP4C and our MOIN server platform. And they use the Panida multiplexer to build up the DAB ensembles and to feed them into the DAB network.
Yeah, thank you, Talk, for the insights. So let's talk about the challenges getting audio from the radio studios to the DAB headend. So the central element, as I said before, is the DAB headend, and it needs to get the content from the radio studios. So now we are focusing on the left part of the diagram here. Yeah, you have to do some considerations about that. So firstly, you have to find out or to design what is the robustness and stability of your IP connection between studios and headend. You have also to consider what is the available capacity on your IP connection between studios and headend, and also whether you would like to have a centralized infrastructure or a decentralized infrastructure where the headend is centralized somewhere and maybe also doing the DAB plus encoding, whereas so in contrast to that, DAB plus encoding can also be performed at the studios, which is then decentralized. And what also plays a role in these considerations is if you only handle in-house audio services, or if you are a network operator and you have third-party service providers delivering their audio feeds from different locations. The point of separation between, or the point of interfacing between Studio and DAB infrastructure is a central element in the considerations, and also which can be a legal or contractual responsibility. Who is responsible for DAB plus encoding? So is it the service provider or is it the multiplex operator? So given these considerations, there are some setups which are most common in the field. The first one is using classical audio over IP. Yeah, the audio needs to get into the software-based encoding multiplexing system. So the remote feeds can be provided over audio over IP, and the DAB plus encoding then takes place at the DAB headend, either as part of the integrated multiplexer system, as it's shown here, or even with dedicated DAB plus encoders. The second common setup is using DAB plus encoders. In this case, the DAB plus encoding takes place at the studio sites, and they directly feed the multiplexer, and the multiplexer just takes the input feeds. Yeah. Finally, sometimes the linear audio signals are available centrally at the headend. In this case, PCM audio can be available and can be directly fed into the multiplexer system. So let's take a very brief journey through our products, which can be used for these setups. So firstly, we have the audio over IP series. This is a series of robust hardware products for professional broadcasting, and with high performance, great audio quality, and so on. And we support a variety of audio interfacing needs, so handling very diverse input sources and also very reliable transmission of these. So here you see 3 models of this series. So we have the IP8E, which is an audio over IP encoder. We have a codec, the IP4C, 4-channel encoder decoder system, and we have an audio over IP decoder for 4 channels, which is the IP4D. Alongside our hardware products, we offer the MOIN system, which is a scalable software solution for audio over IP applications. In contrast to the hardware products, MOIN uses virtualized IT-based infrastructure to give broadcasters a flexible and scalable platform for managing audio contribution and distribution in IP networks. The software differs from the IP hardware series mainly due to its increased scalability of channels. So it's not a hardware box, but it can be flexibly operated on IT servers, for example, in the network operators' facilities or even in the cloud. MOIN, as well as the hardware products, supports a variety of protocols and audio codecs. And speaking of these, of course, also DAB Plus and the transport protocols, which we will have a look on later. So let's jump into the first method of getting audio to the DAB headend, which is audio over IP. Before I hand over to Torg for the demonstration, I would like to show the principle. So the principle is that you have audio over IP encoding at the studio sites, transmit the audio streams through the contribution network to the DAB headend, where some sort of transcoding has to take place because the encoded audio is not compatible to the DAB system. So there needs to be audio decoding and re-encoding for DAB Plus at the headend, and which means that you always have some so-called tandem coding. This example shows that you how it is done for the Akiva system talk explained before. So a number of IP8E encoders are at the studio sites. There they deliver their audio feeds to a software-based decoding system which decodes to PCM audio, which is then fed into the multiplexers as AES 67 streams. The DAB Plus encoding itself is performed at the Paneda multiplexer as a part of that multiplexer system. So as we are talking about comparing the different methods, so in which case a setup as shown here is a good idea. First point is interoperability. Audio streaming using RTP provides you with a broad compatibility across different manufacturers. And second, the reliable performance audio over IP is reliable even in challenging network conditions. It has an independent buffer handling. You can use established secure and robust transport mechanisms like SRT or RIST. Another advantage is that it is 100% independent from the DAB multiplex configuration. And this leads also to the next point. You have a clear separation between the DAB network operator operating the DAB multiplexer and the service providers. You can operate two independent infrastructures which do not have any interdependencies. And last point is multi-purpose. So you can use the audio feeds which are received from the studios also for other purposes like FM distributions, like web streaming, and so on. It is not specific to DAB. So now we are coming to talks demonstration.
Okay, I'll take over. Thank you, Arne. I'll just
You're welcome.
share my screen. So we get to our first demo. It's the audio over IP setup, which is used for the Akiva rollout. It's a little bit simplified, but I can show you now how the setup works in detail. At the regional studios, different input sources are used, of course. It's not only digital audio, it's also AS67 streams and so on. And the IP4C, what it does is basically it's a normal audio over IP encoder. So it does not do a DAB encoding, it just uses a normal audio encoding. Akiva uses a lot eRPTX because that gives a good quality. And which is really nice about the setup is that you have all the possibilities of the audio over IP protocol stack. So you can use dual stream, you can use RIST or SRT for security, and that's built into the audio over IP stack. Basically, Akiva is sending a dual stream and is encoding basically in eRPTX. Then this two streams, two flows are sent to a MOIN server, and the MOIN server does a transcoding. So it transcodes this dual flow eIPTX to PCM, and then outputs an AES67 stream. And this AES67 stream is received from the DAB multiplexer, which is a Pineda multiplexer. And then the DAB audio encoding is placed in the Pineda multiplexer. Then the EDI feed coming out of the multiplexer is sent to various DAB4C, which convert IP EDI to E1 transport-based ETI. And also these services that are sent out from the DAB transmitter can be monitored through a DAB monitoring device. I'll show you now a basic setup of our audio encoder IP4C. So I got now a first demo of our audio IP4C device. Our audio IP4C device has, as the name 4C states, 4 encoder instances, and you can configure these encoders at the codec web page. And basically what you can do is that you have a lot of choices to configure your audio or IP setup. So you can choose between a lot of input sources. That's the second tab here, input sources. So all these input sources are available for DAB encoding and audio encoding. You can choose between normal XLA interfaces. You can encode ISCAR streams. You can encode or transcode elementary streams. You can input also transport streams through example satellite or ASI or IP. Can use RCT or even zip connections. All these input sources are available as input sources. And these input sources can be configured for an encoder instance. And then you can choose which codec the encoder uses. We do this by configuring a profile. That's the first step that we have. And as we said, we support a lot of different codec formats. So basically you have the choice which codec fits best to your network and to your needs. So the main goal that we have with the IP4C is to support all available protocols in a standardized way. So that's really our goal, to support all protocols that are available on the market, so that you have the choice which codec you can use. For Akiva, they choose eIPTX, and so I'll show you now one setup which is used. It's for audio encoder 4, so it's audio input 1, and the profile is eIPTX in that case. And this audio encoder 4 is sent out as an elementary stream. And for the elementary stream, you have all the choices for sending out the elementary stream that's available from the audio of IP stack. So basically, it's sent out as an RTP stream, and you can activate a dual streaming so that 2 flows are sent to the MOIN, and you can activate forward error correction so that when you have some problems on your IP network, that packets can be repaired through FEC process. Or you can top that and activate some of the newer technologies like RIST or SRT, which basically RIST and SRT are working in that way that the decoder sees when packets are missing, and these missed packets are then send back from the encoder to the decoder again through a special protocol, and you can use RIST or SRT for that. So packets can be requested from the decoder if they are missing, and the encoder receives that request and sends these packets again to the decoder through that mechanism. It's RIST or SRT. This dual flow is sent to our MOIN, which I can show you here. MOIN is our server-based solution. It has one decoder configured, and I just show you the detail about the state, how the stream is received. So the decoder receives an AIPTX stream, builds up the configured buffer, and gives you some information about the IP stream that is received, how many packets are received, gives some info about the jitter, how many packets are missed, what's the packet error rate, are there any timed outs, or even duplicates or reorders, how long is the connection up and running. And it does that for both IP feeds, and we have additional requests through our RIST process and our FEC, so that you can see if the FEC is working and how many packets can be recovered or unrecovered, or if RIST is requesting or retransmitted packets. In this setup, the two streams that are received from the dual stream are just decoded and then sent out as an AES67 stream, which can be configured here. And this AES67 stream is received from the Panida multiplexer. I'll just go again to the overview, so that you know where our setup, where we are in our setup. We have just shown briefly the IP4C, which is sending dual flow to the MOIN. MOIN is sending out an AES67 stream, and the Panida multiplexer is receiving this AES67 stream, and then it does the DAB audio encoding inside of the DAB multiplexer. The PAT, which is generated also for the DAB servers, is generated locally at the DAB multiplexer in that case. So I'll just show you briefly the Panida multiplexer. The Panida is receiving or has a service configuration available, which is just one service. It's our IP4C MOIN stream that is received. And we have only one service configured at the moment, and the audio source is the IP4C audio source. And here the DAB audio encoding takes place. To sum up this configuration, I just show you our DAB monitoring device at the end of our chain, which is receiving one feed. It's the feed that's going through all the chain that is described in the document. Just receives one audio services and listens to that audio service and monitors the quality of the service. So basically you can here see, okay, audio is coming in, what is the dynamic label, and you can also check about the slideshow transformation which is coming in. So I think this gives you briefly an introduction about the setup that is Akiva using.
Thank you, Tork. So this was the first of the two methods we wanted to show. So yeah, the second method is DAB plus encoding at the studios. So what is different in this case? In this case, the contribution system is an integral part of the DAB system. It avoids the tandem coding, which we have seen in the other method before. At the other side, you have to take some aspects into account about synchronization and also the DAB structure and framing. And also using specific protocols for the interconnection of encoders and multiplexer. On the topic of what's different in DAB Plus compared to other audio encoding, because we are in principle we are talking about audio encoding here, but DAB Plus has some differences. So it uses high efficiency AAC V2 as it's specified in the DAB in the MPEG-4 standards, which means MPEG-4 AAC, SBR, parametric stereo, as they are also widely used in many other applications like streaming or TV broadcasting. However, for DAB, some adaptations and restrictions were needed to integrate this codec into the system architecture. So firstly, the bitrate can be maximal 192 kilobit per second, and only the audio sampling rates 48 or 32 kilohertz are allowed. But the most relevant modification is to adapt the framing of AAC to that of DAB. DAB frames have a length of 24 milliseconds. In contrast, the regular AAC low complexity processes frames of 1024 samples. For high efficiency AAC, it's 2048 samples. And this corresponds to 21.333 and so on milliseconds. This will not match the DAB framing, so something has to be done. You have to find a common denominator to match the different framings. To do that, first, DAB Plus uses different frame lengths. It uses 960 samples for for AAC low complexity and 1920 for high efficiency AAC. Second, a number of audio frames is combined to a so-called audio superframe. And the number of audio frames depends on the audio sampling rates, so whether it's 48 or 32 kilohertz, and whether it's AAC low complexity or high efficiency AAC. So here we are looking at high efficiency AAC in our example and 48 kilohertz. And in this case, 3 audio frames form a so-called superframe. If AAC low complexity would be used, we would have 6 audio frames per superframe because the audio frame is only 960 samples long. Superframes always have a length of 120 milliseconds. If you transmit that in DAB, this can be divided in the number of 5 DAB frames of 24 milliseconds. So these are the main differences of DAB Plus audio encoding compared to other applications. What's also important to consider is the interfacing between audio encoders and multiplexer. So DAB uses specific protocols. They are mostly based on the DCP protocol, distribution and communications protocol, and they can carry EDI, ETI, which is the same interface as is also used for DAB distribution to the transmitter. It can be the service transport interface, which is specific for encoder interfacing. And it can be also vendor specific, for example, the Fraunhofer MUX-ENC protocol. So when and why should I use dedicated DAB encoders for getting the audio to the head end? They are best if you have DAB-specific ecosystems. You avoid tandem coding of the audio because you directly encode and keep the native DAB Plus subchannel already with the first step. You can have some bitrate savings for the studio feeds because you don't have this tandem coding, and you need no quality overhead for the feeds before it's finally encoded for DAB+. You can gain full control over the DAB+ encoder parameters if you use protocols like the Fraunhofer MUX-Enc protocol, or if you use our REST API for our DAB+ encoder. And also DAB DCP provides some kind of robust connection which is optimized for DAB infrastructures. And it uses forward error correction, packet spreading, resend. And as we have done that also for the transmitter feeds, it can also be considered to use the SRT protocol also for encoder feeds. In our products, the DAB+ encoder is a flexible software module that integrates the DAB+ encoding into different products and allows the broadcasters to encode directly in the native DAB+ format. It uses the Fraunhofer DAB+ encoding library, and it can use EDI STID or EDI ETI to the multiplexer. It supports the local insertion of program-associated data, which is, for example, the dynamic labels or the slideshow, which you often see in DAB. And optionally, it also supports direct connection to the Fraunhofer DAB content server system with the MUX-Enc protocol, where configuration, PID insertion, and monitoring are handled by the multiplexer, and the encoder is controlled by the multiplexer. Yeah, whether you prefer hardware or software-based solutions, we have different possibilities for DAB+ encoding. The 8E, IP8E, which you see in the middle, is a good choice for high-density DAB+ encoding. You can also use the software-based MOIN system for a scalable IP-based infrastructure. And you can also use the flexibility of our IP4C audio codec with different input formats like satellite tuners, DAB tuner, and so on. Flexible backup sources which can be automatically fail over. You can also use our IP4C codec for DAB+. For the IP8E audio encoder, we also offer a variant which is specific to DAB+. It is a dedicated DAB+ encoder with 1 to 8 channels at a competitive price. So we call it IP8E DAB+ edition. And it includes, as you can see here, it includes the DAB+ encoder and the DAB output format to the multiplexer, which you require for this application. Yeah, having said this, I would like to hand over to Torg again for a demonstration of the DAB+ encoder.
Okay, thank you, Arne. And we come to our second demo. It's DAB audio. Instead of using AoIP, we are now in the DAB audio world. So I just want to show you demonstration with our MOIN server, which is a server-based solution. And the best of the MOIN server is the scalability. So as it is a server solution, it is very scalable. So you can receive AS67 streams as input and encode these AS67 streams directly into DAB audio, and then transport the DAB audio through DAB protocols that use the DCP standards to the multiplexer. And as we are, as I said, that we support a lot of protocols. Also, interoperability is a main goal. So the first example I showed you was with a Panida multiplexer, and this example I show you with EZT or Fraunhofer multiplexer. So we always test our applications with different multiplexers so that we know, okay, we are interoperable to each multiplexer that is available on the market. So I just go to the Moin, and what's really nice is that these encoders, I've now built up 12 encoders. These encoders can be upscaled or downscaled through licenses. So the server is a very cost-effective solution. So if you have a server in your regional studio, or at your deployment, you can just simply add a Moin software container to the server and then define how many encoders you will run. And for the codec, it is nearly the same page for the audio encoders. So basically, what you can have as input is A67 streams, which you can define at the interface settings. Audio is 67 input streams. Here there are up to 12 A67 streams available, but all other kind of IP inputs are also available. So elementary stream for transcoding or shoutcast streams and so on. And for the encoder, it's basically the same configuration. So you have the input sources available. Now we use A67 streams, but also live wire or elementary stream, and all other kinds of IP input is available. And then we encode directly to a Fraunhofer DAB format. So as you have seen before, for profiles, we can define the audio codec, and basically for audio over IP, all these other audio IP codecs are available, but we can also use Fraunhofer DAB Plus, as Arne has shown in the DAB audio frame example, which is professional Fraunhofer solutions for DAB encoding. And up to 12 encoder are available. And typically, what you can do is that you that's the DAB submax feature. So basically, what you want to do is that you have many audio encoder inputs. For example, I've set up 2 inputs, and you want to sum or to have one stream for both inputs. So basically, you can define submax, add amount of subchannel you need, and then stream one feed that's, for example, this submax output that contains data for encoder 1 and encoder 2. So basically, 2 DAB audio services are multiplexed in the per DCP standard and sent out as one stream to the multiplexer. And this is now done. So it has one submax that has encoder 1 and encoder 2 as submax payload content, and then it streams out the submax to the EZT multiplexer. And at the Moin, you can define up to 8 submultiplexers that you can choose from the audio encoders. So I've just as a demo here is a submax 2 with encoder 3 and 4, but you can also add subchannels and configure it in that variety you want to use for your network. And the stream that's sent out per DCP standard, the submax output stream, is then received at the IZT mux. There is a special auto mechanism that detects the incoming stream. So that's really nice. So I've now pre-configured the multicast IP that the stream uses, and then you can just simply receive decode EDI data. So I just press that button, then it listens to the stream, and then you can see, okay, the submux is sending out two streams. It's subchannel 1, 0, and 1, and everything is okay. It's error level 0, no detectable errors. And for that multiplex configuration, we take out the subchannel 1 from the submux that is received by the EZT multiplexer, and we use that as input for our DAB multiplex configuration. So I have one example here where we have 3 services, and the DAB service to WCOM Franken is uses the subchannel 1 from the stream that is sent out from the MOIN. So this chain is received or going through our DAB4C and transmitted chain and can be received by our monitoring device A30, and you can listen to that stream and check the slideshow and verify the setup is, for example, working. One thing that's also different to the setup I've shown before for the audio IP is the PAD data. Here in this example, and that can be configured in the multiplexer if the PAD data is coming from the multiplexer or the PAD data is generated at the device that's sitting in the regional studio. Here, in our example for the encoder, the PAD data is generated directly at the MOIN. So we have a configuration that's called local PAD. And we have PAD configuration. And for DAB configuration, you can define the dynamic labels. So basically, you can add a static label, or you can have the dynamic label updated from a file that's fetched from a server, or you can have the DLAs update through SFTP so that you change the text file for the dynamic label directly on the device and then replacing its content to have a dynamic label. And you can also add or delete slideshows through our SFTP servers on that device. So, for example, here encoder 2 uses test DAB submux config and has a slideshow from the Times Radio and just verifying with our 30, okay, dynamic label, it's the same, and it uses Times Radio as a slideshow. So that's the second demo that we want to demonstrate, to have a MOIN with a variety of A67 inputs, then directly encoding into the DAB audio, and then using one or many audio services in one stream, in one DCP stream, sent to a DME multiplexer of now EZT, or Fraunhofer multiplexer, and then this is sending out the DAB multiplexer that is going through our DAB chain and then received by our A30 monitoring device. So I'll hand over back to Arne again.
Yeah, basically we can just continue with the third demo and the Fraunhofer MUX protocol.
Okay, great. We'll just add this demo on top. So we have a third demo prepared, and that's FHG MUX-ENG protocol. The setup is also working with the EZT multiplexer. FHG MUX-ENG protocol is a proprietary protocol used from Fraunhofer, and our IP4C hardware devices or MOIN devices are compatible to the MUX-ENG protocol. And through the MUX-ENG protocol, not only the audio frames, DAB audio frames are sent, also it's a control channel included. So the DAB multiplexer can, for example, do dynamic reconfigurations through the MUX-ENC protocol. And it's the MUX-ENC protocol is also used to send the PID data that is generated at the DAB multiplexer back to the audio encoder, and the PID data is inserted into the DAB audio frames through the MUX-ENC protocol. So PID data is generated at the DAB multiplexer, sent back from the DAB multiplexer to the audio encoding device through the MUX-ENC protocol. I'll just go to the IP4C again. So in our demo, we have audio input 1, encoder 1, which is using the FAG MUX-ENC as PID source, and has a DAB profile which can be reconfigured by the DAB multiplexer. So this profile I'll show you. This as a demo, that this codec can be reconfigured through the FAG MUX-ENC protocol. And what we have as encoder output is that we need a login for the stream, so that the multiplexer knows, okay, I can send configurations to this device, and this device is accepting these weekly configurations. And then we have basically two configurations. We have one for the control connection that's sending the commands for the configuration and the PID data. And we have one configuration for the DAB audio frames that are sent to the multiplexer. So this is now configured that it's listening on the correct IP addresses for control and data. And on the overview, you can show for encoder 1 that it has a control connection to a multiplexer called TVC1, and it's receiving control data and sending out DAB audio frames. So on the multiplexer, if you go to the service component editor, I know I have to change it on the multiplex editor.
Mm-hmm.
One moment, yes.
Right.
There I can check about the services that are configured. The first example, we use the Tuvicom Franken setup. Let's see. I know we use the ETI Tuvicom subchannel 1 submax configuration. Okay.
Right.
Right, and now we want this configuration that is set up is running through the MUX-ENC protocol. So now a subchannel bitrate of 160 kilobit per second is configured, and as we check on the device, okay, 160 kilobits, that's the bitrate that is configured for the DAB servers. And if the multiplex administrator wants to change this configuration or do a dynamic reconfiguration because some services are added and now 160 is not available in the new configuration, you can just change it to, for example, 96 kilobit per second. Then you can save this configuration. And then the configuration is just here received. And as we now can see, okay, that was really short. Now it's from 160 to 96 milliseconds is changed the reconfiguration. And this is seamlessly directly reconfigured by the IZT multiplexer. And for the PID data, we can see that if we have a status for the PID data, we can see that for encoder 1, PID data is received and processed through the MUX-ENC protocol for encoder 1. And if we listen again to the A30, which has 3 services configured. First service was the submux configuration. And now I change over to the servers that we just recently reconfigured. So I changed to WCOM Franken again through the DAB tuner setup. Moment. Yeah, there it is. Further radio.
The other stations.
Other station. Ah, okay.
Yeah.
I think I did just mistake. Wait a moment. Let's see. Was it there? I'm not sure at the moment, but I'll just do a check once again.
Franken it is.
Franken it is.
Mm-hmm.
Okay. It's this one. Okay, I think I've labeled it falsely here. Okay,
Yeah,
there it is.
Yeah.
Okay, I've done a false labeling here for
Mhm.
the DAB tuner, but I
here.
think all right. So you can see, okay, now to become Franken it is, as Arne mentioned. Thank you, Arne. And dynamic label is coming in, and yeah, audio is received, and everything is working on the setup, and it's 96 kilobit as we have done in the reconfiguration. Okay, I think this sums up our demos. So as you see, we support, we have interoperability, and we support a lot of different protocols and standards that can be used for your setup.
Yeah, thank you, Talk. I will just run over the remaining slides just as a summary, if they are coming. So here we are. Yeah, I just want to briefly mention, so Talk has already covered it partly. An additional thing is using local audio at the DAB headend. So when linear audio is available, this can be AES, EBU, or analog audio. In our case here it is EBU. You can use our IP8i AES627 gateways to, as a gateway between the linear audio and the multiplexer system. The special audio, this is what Talk has already explained before. You can use all the different special audio sources of the IP4C, like satellite tuners, if you have existing audio distribution over satellite. I'm coming to the conclusion. So we have comprehensive solutions for variety of scenarios. Including audio over IP, DAB+ encoders, and interfacing linear audio over AES67. Our IP series and our MOIN platform as hardware and software solutions as a platform for audio over IP and DAB+ encoding. And this all ensures a seamless integration into your infrastructures. And just as an outlook, our DAB roadmap, what we have just released for DAB distribution over unstable networks, is EDI over SRT. And we are working on concepts for EDI decoding and monitoring. So stay tuned about this. So thank you very much for your time. We are a bit over. However, I would like to have a look into the chat for the questions which have been sent. And it's about possible PAD data flows. So this is basically what Talk has already explained in the demonstration. You have different possibilities. You can use the multiplexer as a gateway, especially, of course, if the DAB encoding takes place in the multiplexer system. You have seen that our DAB+ encoders also allow direct local insertion of PAD data. There are different possibilities. If you would like to know more about that, yeah, just contact us, and we will give you some more insight about that. So, having said that, I would like to say thank you for your attendance.
One question was there, which was coming from Robert.
Yeah, do you have possible concepts for dynamic reconfigurations in our third setup? So this means
yes,
the third multiplex.
Yeah, we have that. I think, Arne, you had one slide about the REST API.
I can go to that slide
that we have on stock.
Yeah.
Because I think Arne can show you that on the slide directly, because we have prepared some extra slides.
Yeah, it's not in here, but the concept is the same. Yeah. Instead of using the Fraunhofer Mux-Enc protocol, the idea is to use the available REST API of our encoders, more in our IP series, and use that for configuration, monitoring, and also data transfer. Last question, next question from Emanuele. Hi, Emanuele, is if it's possible to use the DAB plus encoding directly on the Palmeda multiplex. So this is something Talk can answer.
Yeah, yeah, we are working closely together with Palmeda, and we have prepared some solutions for that, which will come in the next months. So we have a close contact, as you know, with Palmeda, and yeah, we'll have something available for solutions.
Yeah, it's mainly a matter of testing, and so before it can be released in the next software releases. Then thank you very much. Have a nice day. Have a nice end of the week tomorrow, and see you.